Thank you, Aniko. Thank you very much for the invitation, Aniko and Dan. I am very happy to be here and excited about this workshop. And I also want to thank Emma, who suggested my name. And Emma suggested that I talk about some challenging modeling problems in atmospheric science that might benefit from new statistics and machine learning techniques. And so today I'm going to talk about one of the most perplexing problems for me, which is the simulation of tropical clouds and climate. Okay, so who am I? I know almost nothing about machine learning and data mining, so if I am imprecise in my terminology, please forgive me. But who I am is a professor in the Department of Atmospheric Science at Colorado State University. There's two other of my colleagues in the room who are in our department, Libby and Peter Jan over there. I have general interests in tropical meteorology, climate dynamics, ocean-atmosphere interaction, and climate modeling. I have spent some time out in the field, and so this is a picture of me a couple of weeks ago sitting on a ship in the tropical Pacific, launching a balloon, and something Jordan is near and dear to her heart too, because she led this effort. So I do go out in the field occasionally, and we also have another field program next summer, but models are pretty much the primary tools that I use. And in my career so far, we've used a broad spectrum of models, ranging from global climate models, such as the NCAR Community Earth System model that's developed here. But I also use other types of models, including regional climate and weather models, sometimes run at relatively fine resolution for us, which is something like 1 kilometer grid spacing. But I also use reduced complexity models, such as linear baroclinic models, very simple one-dimensional ocean models, and even more stripped down, I've developed theoretical models, like a model called the moisture mode model with a colleague at Columbia named Adam Sobel. So anyways, models are sort of my world, but one of the troublesome things about modeling, particularly the tropics, are clouds. And so clouds are nettlesome. They occur at smaller scales than the grid scale, especially for problems related to global climate modeling. The distributions are complex. They evolve rapidly, but then the key to much of what I'm going to talk about here is that they also feed back strongly onto the atmosphere. So next few slides are just going to be some motivation, some pretty cloud pictures basically, before I get to some of the more important consequences. So this is a scene out in the middle of the Pacific that we experienced a few weeks ago. Very calm days sometimes where the ocean is like glass. So one type of cloud that you often see in the tropics are sort of these shallow, convective or cumulus congestus clouds like this. These are relatively small scale. They might not seem terribly significant, but they're actually very important from the standpoint of simulating climate. Am I doing something wrong? Because they're a major means of moisture transport from the atmospheric boundary layer into higher parts of the atmosphere. So they're a major moisture source for areas of the atmosphere like 1.5 kilometers above the surface. And so, for example, you can see this picture here of a shallow cloud field with one of the clouds dissipating, and it sort of looks like a ghost turret, and that cloud is leaving its moisture behind and moistening the lower troposphere. So shallow clouds are important, but we also, of course, in the tropics have these deeper convective clouds that can go all the way up to the tropopause, the region between the troposphere and the stratosphere. And these clouds are extremely important also because they essentially determine the temperature structure of the tropics, how temperature changes with height in the tropics. So we have to simulate these properly as well. And then, of course, sometimes the cloud field is extremely complex. And so, this is an example of a cloud that we typically call a stratiform, cloud that is lightly precipitating out of an anvil. And you can also see, however, a shallower cloud field that exists at the same time. So often there's a lot of complexity, a lot of different cloud types that we see in the tropical atmosphere. And many of these, most of these cloud types occur at scales much, much smaller than the scales we can resolve in a global climate model. Colder regions of the tropics have their own set of issues, and so for colder regions of the tropics, I'm thinking like equatorial regions near South America, equatorial regions off the west coast of Africa. Clouds in those regions tend to be more layered, and so we get a cloud type that is typically called stratocumulus, where you have lower layered clouds. This is a cloud field we actually saw in the West Pacific that started to look sort of like that. As some evidence that these clouds are, stratocumulus clouds in colder ocean regions are really low. Ignore the topography because this is false advertising. This is Northern California. It's not a cold tropical region, but you have similar clouds, down near the equator as well. You can see that there are extensive low cloud fields extending off the coast of in this case, North America here. And as evidence that these cloud fields are really low, and I don't know if you can really see this that well on this screen here, but there's a smoke plume actually wafting over this cloud deck that came from the Biscuit Fire in southwest Oregon here in mid 2002. So these low cloud fields, as I'll mention later, are also extremely important for climate because they're highly reflective. And so if you did not have these cloud fields off the coasts of continents, then there would be much more sunlight penetrating to the ocean surface and being absorbed by the ocean. So these are very important for regulating the energy balance of the planet. Okay, so as I mentioned, clouds often occur, and most often occur at scales much, much smaller that can be resolved by a climate model. And so we have to resort to processes called parameterization in order to represent clouds and their interactions with the environment. So the technical definition for parameterization that the American Meteorological Society gives, and this is from their glossary, is the representation in a dynamic model of physical effects in terms of admittedly oversimplified parameters rather than realistically requiring such effects to be consequences of the dynamics of the system. So things like clouds at scales which can't be represented directly by a coarse resolution model must be parameterized. But it's not only clouds and convection in global models that must be parameterized. We also have to parameterize radiation and its interactions with trace gases, clouds, and aerosols. We have to parameterize exchanges of heat, moisture, and momentum between the atmosphere and ocean and land surfaces. We have to parameterize the atmospheric boundary layer, the lowest kilometer or two of the atmosphere. And there's other things that we also have to parameterize, for example, mountain waves that we see around here. We often have to parameterize things like that. But clouds and convection are sort of near and dear to my heart, and I think they're the most critical problem in terms of a parameterization problem that we have, at least in atmospheric science in the context of climate modeling. Okay, so this is the basic problem. So a typical global climate model nowadays has something like 100 kilometer by 100 kilometer grid cells. And if you look at a cloud field, you often see, for example, I took this from a GOES-16 satellite image over the East Pacific yesterday. You often see this as a very complex cloud field that exists within this larger grid box. So what cumulus parameterizations do, so we're thinking about deeper clouds now, is that they typically take sort of the grid scale average humidity and temperature data from a column of grid cells, and then this parameterization statistically represents the population of clouds that might exist within that column of cells, and then determines how that population of clouds then feeds back to the grid scale temperature and humidity. So traditionally what you get out of a parameterization is a temperature tendency and a moisture tendency that is generated by the cloud field, and then that is able to change the grid average temperature and humidity field. You could do also momentum if you wanted to, if you could make more, add more tendencies that cloud fields represent, but most climate models simply spit out a temperature and moisture tendency. Many climate model schemes, including actually the one that is used for deep convection here in the NCAR model, are based on early work by Akio Arakawa and Wayne Schubert at UCLA in the early 1970s. There's a famous cumulus parameterization called Arakawa and Schubert that is the basis of still many parameterizations that we see out there in the climate modeling community today, including, as I mentioned, at NCAR. So there's lots of assumptions, obviously, that go into these parameterizations, and I'm going to show you some examples of how imperfection in these parameterizations affect climate simulations. So low clouds also have their own set of problems. So this is a stratocumulus or low cloud deck scene, for example, in cold tropical ocean areas. And there are a similarly complex set of parameterization issues that go into simulating low clouds. So for example, you have to take into account radiation at the top of the clouds. You have to take into account entrainment of air from above the boundary layer into the cloudy region. You have to account for turbulent mixing in the boundary layer. There's drizzle that rains out moisture, surface fluxes, and so there's a lot that goes into development of a cloud parameterization. So those have their, low clouds have their own unique set of parameterization issues. One thing I won't talk about is that there are some recent approaches that are beginning to unify treatments of low clouds and high clouds. For example, there's a scheme in the NCAR model right now called CLUB that tries to seamlessly predict the evolution from low clouds to high clouds in places like the tropics, but I won't talk too much more about that. Okay, so what are some consequences of poor and imperfect cloud parameterization? So I'm going to talk about a few different examples here. So one example that is actually near and dear to my heart is a phenomenon called the Madden-Julian oscillation. And so I actually did my PhD dissertation on this phenomenon. So what is shown here is sort of a whole life cycle of the Madden-Julian oscillation, and this animation here takes something like 48 days, and so you can see time ticking around on the upper right of this plot. So what this phenomenon is it's associated with, these blue curls will pop up here, a blow up of precipitation in the Indian Ocean that then moves very slowly off towards the east with time and reaches the West Pacific, and then there's a similar suppressed region of precipitation that follows it. And again, this whole life cycle takes something like 50 days or so to complete. And I'll show you in the next plot, this disturbance is also associated with wind anomalies that propagate not only to other regions of the tropics, but also the higher latitudes where we live. So this phenomenon was discovered actually at NCAR by NCAR scientists in the early 1970s. Roland Madden and Paul Julian were NCAR scientists at the time. And its physics are still somewhat mysterious, but one thing that we do know about this phenomenon is that climate models have a very difficult time simulating it, and it has to do with, for reasons I'll talk about later, deficiencies in the simulation of clouds and models. Okay, so why is the MJO important? One thing that the MJO does is it teleconnects to other parts of the tropics, and so, for example, this top plot shows a state where the precipitation center associated with the MJO has reached the Western Pacific Ocean. We were sitting on our boat like right over here last week, so sort of in the vicinity of this. And this disturbance sends out wind anomalies that reach the coast of the Americas. So it's not just centered over sort of the Indo-Pacific warm pool, but it actually sends out winds across much of the tropics. And one of the consequences of this is that there is a modulation of hurricane activity by this disturbance, depending on what phase it's in. And so when winds over the Atlantic, Gulf of Mexico, and Caribbean Sea are from the west, you tend to get a fourfold increase in hurricane activity versus periods when the wind is from the east. And we've and others have actually exploited this modulation of hurricane activity by the MJO using things like logistic regression techniques to actually do forecasts of MJO activity or hurricane activity based on the MJO as a predictor. So we've done some work on that, which I won't talk about any further here. But another thing that the MJO also does, and this is something that's near and dear to not only my heart, but Libby's heart in this room, and my animation, there's my animation, is that the MJO also connects to higher latitudes. And so this is a figure that was generated by Christiana Stan and a few other authors, including me, showing how when MJO precipitation is here in the Western Pacific, it has connections to other parts of the globe. And one of the things that it affects are things called atmospheric rivers, which I notice is a topic of some people's interest here at this meeting. This is an example of an atmospheric river, a plume of very high integrated water vapor that, for example, runs into the coastal mountains of California and Sierra Nevadas and produces quite a bit of rainfall. I can't remember exactly what this event was. Could have been the Oroville Dam flooding event, I'm not sure. But these are very important for weather in places like California. So one of the things that Libby and our students and me have been doing is that we've been looking at how the MJO modulates atmospheric river activity. And so, this is an example of some work that Brian Mudhank did, showing that certain phases of the MJO are associated with an increase in California atmospheric river activity. And we've even gone a step further than this, and we've actually employed information on the MJO modulation and also information on a phenomenon called a quasi-biennial oscillation to form prediction models for atmospheric river activity. And we can actually show skill at predicting atmospheric rivers in places like California out like a month in advance, or sort of that scale. So pretty successful. So as I mentioned, the MJO is poorly simulated by many climate models. There's a lot of stuff here, but let me just point you first to these top two plots. These are sort of an observational representation of MJO type variability. Longitude along the equator is on this axis, and time is on this axis. So this is going from minus 30 days to a lag of plus 30 days. What you can see here is that if you think about longitudes and time, in observations, the MJO propagates eastward along the equator, which is consistent with that animation that I showed you. But then if you look at some climate models, for example, these two panels here on the left-hand side, these are climate models. One is a older version of the GFDL model, and this is a Korean model. And these models show that in their model, the MJO propagates the wrong direction. So that's obviously a pretty poor simulation of the MJO. Now, in the community, I've done some work on this, and others have done some work on this. You can do simple things to climate models to make them produce better MJO. So for example, you can do simple fixes that make atmospheric convection more sensitive to humidity, atmospheric moisture. And these two models here are an example of when we did some simple fixes, and you could see here that the MJO propagates eastward in these models now. So that seems good, but the problem is always that making these simple fixes degrades other aspects of the simulation. So for example, This is May through October long-term average precipitation. This is an observational product here, and then we have these different models, these 4 panels associated with these different models here. And so you could see that the precipitation in the mean for summertime is horrific in these models where we've made these simple fixes. There's a feature, let's see if I can get my cursor back, here that people often call the Great Red Spot sitting over the Northwest Pacific that shows up in many of these simulations where you make simple fixes to humidity. So if you're going to be doing climate simulations, you obviously do not want horrific precipitation distributions that look like this. Let's see. There's other issues with cloud parameterizations that also produce other biases. So, for example, simulation of monsoons is often deficient in climate models. We have a monsoon in the southwestern United States, and so, for example, if you look in this lower left plot, each of these lines shows the average onset date of the North American monsoon. So it starts in early June down here and then goes through July once you get up here into Arizona and New Mexico. It's kind of a funky plot if you actually look at what these numbers are, because there's things coming in different directions, but generally the monsoon onset goes from south to north. And climate models don't seem to do a very good job of this. This is on the upper right, again, an observational plot of precipitation. So latitude is on the left, and month is actually on the x-axis here. So what we've done is we've looked at a particular zone of longitudes in the western United States. So taken, a zone of longitudes, where the monsoon affects the western United States, and have tracked the precipitation climatology in this plot as a function of latitude. And what you could see here is in climate models, and so the middle panel here is a multi-model mean from the last generation of climate models used for the Intergovernmental Panel on Climate Change Assessment Report. And the bottom panel is the difference between these climate models and observations. And what you could see here is that on average, models tend to have too late of an onset of the North American monsoon, and they tend to persist the monsoon too late into the fall, so October through December. So this is very important for people thinking about water resources in the southwestern United States, and ameliorating biases like this would produce more confidence in future projections of climate change under greenhouse gas scenarios. And so this is another critical bias for water resources in places like Los Angeles and Phoenix and things like that. Okay, so one more consequence of poor cloud parameterizations are these low cloud regions off the coast, for example, of the Americas. This plot is actually a plot that was generated by my former advisor, Dennis Hartman, at the University of Washington, showing the effect of clouds on the radiative energy budget of the atmosphere at various locations. So I want to point out the regions that I have in arrows here. These regions are areas of low cloudiness, those stratocumulus clouds that I showed before. And the blue colors on here are indicating something that we call negative cloud forcing. And so you could see that these values are something like minus 50, minus 60 watts per meter squared in these blue areas off the coast. And what this quantity is basically telling us is how much less energy is coming into the climate system due to the presence of clouds versus if you had gotten rid of clouds and let that radiation penetrate to the ocean surface. So these clouds in these regions are causing 50, 60 watts per meter squared less of solar energy coming into the climate system versus if they didn't exist. So that's what that is saying. So these are an important regulatory mechanism for the Earth's climate system and the Earth's energy budget. So it's important that we get these clouds right. It is also important, for reasons I'll talk about later, that we're also able to predict what these clouds are going to do in a warmer climate. Are these cloud areas going to expand in areal extent? Are they going to contract in areal extent? Those have very important consequences for the energy budget in the future. So how well do our clouds simulated in models in these low cloud regions? It turns out not terribly well. So this is a plot by Lin et al. 2014 showing the observed percent cloudiness from a product called ISKIP. And you can see here, and this is the coast of South America, right here, that I'm pointing out in my cursor. You can see that low clouds cover something on the order of 70 to 80% of the area. If you took a grid box, for example, off the coast of South America. But if you look at climate models, and this is a series of climate models again from that last assessment report, you can see that the climate models are all over the place. And so you see that some climate models have very little low cloud in this region. Others have greater amounts of low cloud. So there's some issues with simulation of low clouds that are very, very important for the radiative energy budget of the planet. Okay, so going forward into the future, why is this important? So this is a plot from the Intergovernmental Panel on Climate Change 2013 report that shows the change in global mean surface temperature for different emission pathways. And so there are 4 different emission pathways listed on here. They're labeled RCP, and then there's a number after it. 8.5, for example, says that there is going to be a forcing of 8.5 watts per meter squared applied to the climate system by the year 2100, essentially due to increases in greenhouse gases. So that's a scenario, that's sort of a business as usual scenario that predicts increasing forcing of greenhouse gases out to the next century. And then the center point on here, the darker line at the middle of each of these distributions, is the multi-model mean surface temperature change. And then there's also a spread on here that gives an indication of the different projected global mean temperatures across different models. So you can see on here, there's a reasonable amount of spread. So, an exaggerated case of this, if we got to 2300, which is way out into the future, I mean, that's sort of sci-fi land. You could see that global models predict anywhere from a 3 degrees Celsius all the way up to a 12 degrees Celsius global mean temperature change. So that's quite a bit of spread. But even if you look at 2100, there's a spread going from something like 2.5 to 5 degrees Celsius global mean temperature warming. There's a discontinuity here at 2100 just because not everybody ran their models past 2100. There's a different set of models if you're wondering about that. So reasonable degree of spread, and it's generally thought in the climate community that this degree of spread among different climate models is primarily due to their treatment of clouds and differing treatment of clouds within the models. So as some more evidence of this, I'm going to show this plot. So let's just concentrate here on this column that says C. And so what C is a column that represents the strength of cloud feedbacks. If you notice here on the y-axis, there's something called the feedback parameter, and the units are watts per meter squared per degree Celsius. So what this feedback parameter represents is how many extra watts per meter squared of energy are going into the climate system for each degree you warm it up due to the presence of a certain factor or the change in a certain factor. So if it's 0, changes, for example, in clouds wouldn't have any impact of either amplifying or damping the warming impact of a greenhouse gas forcing. So what you see here is for clouds, there's actually a reasonable amount of spread across different climate models, and each of these symbols is a different climate model, in what they say clouds are going to do to the climate system. So there's some models here, like this purple one, which I think is a French model, IPSL, that says that clouds are going to add an extra 1 watt per meter squared of energy into the climate system for each degree you warm it up. Whereas there are other models like this blue one down here that actually say that clouds are going to be a negative feedback. So if you warm up the climate, clouds are going to change in such a way such that less energy is put into the climate system due to the presence or changes in clouds. So how clouds might act in different ways, depending on what model you look at, might be through a variety of different things. But one thing I talked about are the low cloud regions before. So if you have a model where the low cloud regions in a warmer climate shrink in areal extent, such that the eastern oceans become less reflective and more sunlight is let into the climate system, then those models would tend to be a positive feedback up here. Whereas other models like this one say you warm up the climate system and clouds in the eastern oceans become thicker and more extensive, that would reflect more sunlight back to space, so that would be a negative feedback. So what this plot is saying is that there's still quite a bit of disagreement in how clouds are going to change in a future climate and how that feedback onto the climate system. There's other feedbacks on here too, which I won't talk about. This is the Planck feedback. Basically, as climate warms, sigma temperature to the fourth, the Earth emits more radiation. There's a feedback in here called the water vapor feedback, which is also dependent on clouds. There's a feedback here called the lapse rate feedback, which is also dependent on clouds, for reasons I talked about at the beginning. So there's a lot on here, and clouds are actually a root of a lot of the uncertainties in these things. Okay, so opportunities for the data science community to engage with the climate science community to solve some of these problems. The first thing I want to point out is something a bit more observational, I guess. So there's a lot of interest in the community lately in the topic of process-oriented diagnostics. And so how I define a process-oriented diagnostic is a diagnostic that characterizes a specific physical process or emergent behavior that is related to the ability of a model to simulate and observe phenomenon. So an example, a very idealized example of how this might work is you might have a target phenomenon on this axis. So for example, ability of a climate model to simulate the MJO, Mann-Julian oscillation. And on this axis, we might have a process-oriented diagnostic or metric that, for example, talks about how sensitive convection is to environmental moisture. Talks about some sort of process level information. And you could use observations to come up with some sort of a truth for where the real world lies. And then you could plot it in dots each of your climate models to see how well it both simulates this target phenomenon and process-oriented diagnostic. So that's one framework. People also use other types of paradigms for this. I mean, there's a lot of work recently done on emergent constraints. Emergent constraints are, the idea is that if a climate model is able to realistically simulate, some process, which might be, a single process or a collection of different processes acting behavior to produce some emergent behavior, then that model is likely better suited to do future projections. So there's a variety of different techniques that, and paradigms people have used, but regardless, there's a lot of interest in the community nowadays of bringing more process-oriented information to bear to model diagnosis. So at the World Meteorological Society level, there's a climate metrics panel that's thinking about this. At Lawrence Berkeley National Lab, there's a PCMDI effort that's thinking about this. And then there's also an effort in the United States that has just started over the last few years called the NOAA MAP Model Diagnostics Task Force, which is a task force which is under a particular program in NOAA that is tasked with developing process-oriented diagnostics to evaluate climate models. And I'm currently the lead of this effort, and just wanted to put out there that there might be some opportunity for the data science community to actually engage within this activity. Okay, so here are some examples of the things that we're diagnosing within climate models. The top few of these are actually related to clouds. So for example, Kenta Suzuki at the University of Tokyo is looking at the ability of climate models to simulate warm clouds that haven't reached the freezing level. David Nealon at UCLA is bringing data to bear on convective onset statistics and see whether models can simulate that properly. The North American monsoon is being diagnosed. Radiative feedbacks and cloud circulation feedbacks are being diagnosed by Bryden Soden at the University of Miami. And there's a whole bunch of other areas that we're looking at as a task force, including weather, typing and extremes, tropical and extratropical cyclones, El Nino teleconnections, land-atmosphere coupling, the MJO, so on and so forth. So I'm currently leading this task force, although David Nealon is going to be taking over next month and leading it going forward. So one of the products that we've developed as a task force is something we call the Model Diagnostics Task Force software package. And essentially, this is this flow diagram describes an open source software package that's based on Python, where each particular diagnostic team plugs in their diagnostics into a particular pod here. So this pod here might be convective transition statistics. This might be weather types. This might be El Nino teleconnections. So each group plugs in their diagnostics into a pod, runs these diagnostics on observations, and looks at the ability of climate models to represent what we see from the observed world. And all of these pods ultimately get spit out into a website here that the community can look at. So this package is currently running at NCAR, and it's also currently running at GFDL, but there's a website that anybody can download this and contribute their particular diagnostic to this framework to bring to bear on climate model evaluation. So this might be an opportunity for engagement more from the observational side from the data science community. And I'd be happy to talk with anybody about this later if you're interested. But there's also direct approaches regarding high resolution modeling that I want to mention. So the latest state of climate modeling, I think, could be nicely represented by this quote from Miyakawa and Sato, 2017. So what it says is that state-of-the-art supercomputers have carried us to a point where global sub-kilometer grid systems are applicable for short simulations of several days, and sub-10 kilometer grid systems can be applied for simulations that are several years long. So we've come a long way in being able to simulate the Earth's climate system with fidelity, but this sort of statement suggests that the cost of doing simulations, particularly if you turn off all of the parameterizations in models and run at high resolution, is still prohibitively expensive to do extended climate simulations that, for example, require you to go out 300 years out into the future, and even more prohibitive if you're going to be thinking about paleoclimate type simulations, which require you to do many orders of magnitude larger than that. So just to show you some examples of where we've gotten with global climate modeling, this is an example of a simulation, a 1 kilometer grid spacing simulation of a Japanese model called NICAM, which produces very, very nice representations of clouds, at least at first glance visually. If you look at it, you could see nice convective organization. You see a tropical cyclone here. If you zoom down and look at the fine scales, you see that vertical structure looks reasonably good. So we can actually do reasonably good cloud simulations on a global scale. The problem is, this simulation was only run for 3 days, and so if you want to do 100-year simulations, this is still prohibitively expensive. Another approach that creates a little bit more computational efficiency is an approach called superparameterization, and the idea here is that, and this was actually an approach that was also developed at NCAR and also filtered into Colorado State University. The idea here is that you have your larger model grid cell that might be 100 kilometers on a side, and superparameterization replaces all of the cloud-related parameterizations within it by embedding a two-dimensional cloud-resolving model within each model grid cell. And so this example here shows basically a curtain of 4 kilometer grid spacing grid cells that are oriented east-west that are used to explicitly simulate clouds. And so this shows a lot of promise for relieving many of the tropical cloud biases, for example, that I talked about before. This sort of approach produces very good Madden-Julian oscillation. It reduces cloud biases in places like the East Pacific. It produces a better El Nino if you couple it. So there's a lot of good stuff that this model does. I won't talk about some of the criticisms of this approach. There are some. But approaches like this produce a lot better simulation of climate. Now the problem still is that this approach is computationally more feasible than resolving than a 1 kilometer mesh applied over the entire globe, because you only basically have a curtain of grid cells within each larger model grid box. But this sort of approach is still orders of magnitude more expensive than a traditional parameterization. So it's still prohibitively difficult to use this sort of model to run out many scenarios over hundreds of years, although we could run 25 years at a time, for example, in time slice type experiments. So these approaches produce serious superior climate simulations, but the viability for climate simulation in the short term is limited, since such simulations are too computationally expensive, at least for the foreseeable future. So how can we get around this, but at the same time getting around some of the pitfalls of parameterization? And like I said, I don't know much about data science, but there are some people in our climate community who have actually thought about sort of hybrid approaches that have actually employed data science. And I'll mention in particular this one particular paper by Rasp et al. 2018 that employs superparameterization to train a neural network and predict tendencies of moisture and temperature associated with clouds. So there's a paper that came out in the Proceedings of the National Academy of Sciences that's called Deep Learning to Represent Subgrid Scale Processes in Climate Models. And basically what they did is they used a deep neural network trained on a version of the SP-CAM, superparameterized community atmosphere model that I just talked about, this curtain of cells, to represent most subgrid scale atmospheric tendencies given an initial atmospheric state. They used a 1-year aquaplanet simulation of the SP-CAM for training. In aquaplanet simulations, you get rid of all continents, all you have is an ocean underneath your atmospheric model. And they used this as a training data set. And they didn't apply any energy constraints, for example, to moist static energy, but they actually found that this model did a reasonable job of conserving moist static energy, which is the sum of latent heat, sensible heat, and potential energy when they ran this model. Although they mentioned that you could also add a correction to make the energy conservation perfect afterwards. What they argued was that this model version using this deep learning approach ran 25 times faster than the version of SPCAM that I showed, which is a very, very good speed up. So it's feasible, rather than using a doing a 25-year simulation, you could do a 20 by 25-year simulation, and get the use the same computing power. So how did this model do? Show you a couple of examples, I think, to wrap up here. This bottom left plot shows, all right, so bottom x-axis here is latitude, and this is pressure. So we're basically going up in height as we go up this plot. And the colors on here are the what we call the zonal mean diabatic heating tendency in various 3 models here. And essentially what this is if you average around an entire latitude belt, you get the zonal mean. And so this shows the latitude averaged mean diabatic heating. The full model SPCAM is shown here, and so you can see here that there's a red area positive diabatic heating right on the equator, which is associated with concentration of deep convection on the equator in a single intertropical convergence zone structure. There's convergence into the tropics, and there's only one center of this in this particular model. This is the neural network trained model right here, and you could see that in the time mean, at least, it does a pretty good job of getting this distribution. And this is a comparison to a traditional parameterized version of the community atmosphere model, and you can see this model gets 2 intertropical convergence zones, so very different behavior. So this model shows a lot of promise. Another thing it shows promise at is getting the Madden-Julian oscillation right. This is a wave number frequency spectrum, so this axis here shows zonal scale. This axis here shows frequency. The Madden-Julian oscillation exists where this little bullseye is here, around units of a value of k equals 2, which basically is 1 wavelength able to fit around the equatorial belt, and then time scales around 30 days or so. And this neural network model does a pretty good job of actually getting this bullseye. The conventional parameterized model doesn't get this, which is endemic to many climate models. So this approach shows a lot of promise. There are some things that it struggles with. It actually struggled when you warmed up the climate outside of conditions in which it was trained, like warmed up the climate by 4 degrees Celsius. It failed to reproduce the SPCAM's simulation at 4 degrees Celsius warmer when you did that. So that's one issue that they noted. They also noted that, especially at lower levels here, this is the mean diabatic heating, but they noted that there was less variability in diabatic heating associated with shallow clouds down near the surface, and so that's something else. They also had trouble with ensuring atmospheric static stability. So the atmosphere often was unrealistically unstable after they applied this approach. But this was a first attempt, and so there's a lot of promise that this paper seemed to show as far as using some of these techniques on training data sets from high-resolution models. Okay, so let me wrap up. So summary and key points here. So the simulation of clouds and convection is a critical challenge to the climate model community that affects the ability to make confident projections. Parameterizations now simulate convection and clouds in most models. Cloud resolving, system resolving, and large eddy simulation approaches do show promise in improving climate simulations, although they are still prohibitively expensive for everyday climate simulations. And so we're still going to need parameterization for the foreseeable future given these costs. And we're not going to be able to do 300-year simulations with 1-kilometer models for the foreseeable future. I showed some examples of deep learning approaches trained at high-resolution data sets that show some promise in creating computational efficiencies. And then I also plugged that there are various efforts on process-oriented diagnostics going on in the community that might help employ data science with observations to aid model diagnosis and improve cloud parameterization. So that's another pathway other than high-resolution data sets. So some things that occurred to me when I was making up this talk, and this is my last slide, is whether or not the methods that this Raspidal study I just showed used with a climate model can actually be used effectively with available observations to develop parameterizations. Observations tend to be very sparse compared to the high-resolution temporal and spatial output you get from a large eddy simulation model, for example. So maybe there's some drawbacks there, but possibly there's something that we could do with observations in order to inform parameterizations offline of high-resolution models. I guess there's also a question that that study brought up is, are the techniques trained on data in current climate applicable to future climates that warm up by 4 or 5 degrees or so? What sorts of physical constraints need to be applied? I think that's an interesting issue to me. I also already mentioned this. And then another thing regarding training on a model is that even though you run your model at high resolution and turn off things like hydrostatic balance and allow convection to be simulated explicitly, there's still things in the model that have to be parameterized, like microphysics. So even though your climate model at high resolution produces a better simulation, you're not necessarily training against reality because there's still things that are parameterized. So that's an issue I think that needs to be kept in mind when applying some of these techniques. Okay, so that's all I had, and thank you very much.